Okay, we are going to start section 7.2 here today, talking about sample proportions. And we're going to need to be accessing a web page that has an applet on it. What we're kind of studying here in this section is this question of what results would I expect to see if I sampled repeatedly from a population of interest. So if we were to keep reaching into a population and drawing out samples, what might be some things that we could possibly learn from that population? And so sampling distributions kind of allow us to draw a conclusion about a population parameter based on an observed statistic, okay, from a sample. Remember, sampling distributions are this notion of continuing to draw into a population and draw out samples of the same size, and you're calculating some type of statistic, either a sample mean, X bar, or a sample proportion of P hat. Okay? So one of the most common statistics that you actually see in media is a sample proportion. So we're going to kind of ask, how good is a sample proportion for estimating what a true population proportion is? Because we know this, we know that a sample proportion, which is what P hat is, that's going to vary from one sample to another sample. Okay? Every time we reach in and we pull out a new sample and we calculate the proportion of whatever the variable is that we're trying to measure, it's going to be slightly different from one sample to another. Now, your variability depends on what your sample size is. Okay, we learned this in the previous section, that if we are taking larger and larger sample sizes, it's going to make our statistic be much more narrow. Okay, it's going to decrease the variability. And so we're going to go to this website that you see that I have highlighted there. It's rossmanchance.com. And so I'm going to go ahead and change my screen over. We're going to change a few settings here. Okay. So along the left side here, you can see this is an applet, which is just a statistical piece of software that lets you kind of run some different simulations. I'm going to reset this here. Okay. I believe that's the normal setting here that we would get when we open up this website. So what we're going to be looking at in this particular applet is kind of one of those candy machines. We're imagining that this is filled with Reese's Pieces candies. And we're interested in trying to measure what is the proportion of orange candies in a sample that we would draw out here. Okay? So what we're going to be doing is we're going to take, actually, if you're going to this website, you would want to change a couple of settings here. We want to definitely change this. I think the original setting here is number of orange. I think that's what the default is. Hang on one second. Sorry.
Walk in an orderly fashion. Do not run. All staff begin lockdown protocols now.
Okay.
Attention all.
So we're going to select a proportion of orange candies. That's what we're interested in, rather than the number of orange candies. Okay, and we're going to say that in this particular candy machine, the actual true proportion of orange candies is 0.45. 45% of the candies that are in this candy machine are orange. That is actually the P, the population proportion. Okay, we want to take samples of size 25 candies. Okay, so I'm going to go ahead and demonstrate this here for you. I'm going to make sure this animate button is selected, and I'm going to go ahead and click summary statistics as well. I'm just going to have one here for the number of samples, and I'm going to click the draw sample button, and you can kind of see the animation there. What it's doing is it's showing you all the candies coming out of the machine, but it's kind of sorting them. On the left side, you can see just the number of candies that were in fact orange from this sample. Okay, now underneath that in blue, you will see what the proportion from that sample of size 25, the proportion of orange candies. So it looks like the proportion of orange candies they're telling us was roughly about 44% of just that one sample were orange. And then they went down here and they put this little tiny dot on the dot plot here. That sample proportion was 44%. Okay. Now, according to our instructions here, and I'll go ahead and kind of fill that in on this blank here. So now, when we all do this, you could run this applet, you could get a slightly different p-hat. I'm just going to fill in what I'm getting as I'm demonstrating this for you. Okay, so this is asking us then to go ahead and draw out 9 more samples. Okay? So you don't have to watch that animation each time. You can see what the total number of samples here. It'll keep a running total. So I'm just going to tap that until I see that my total is 10. Okay? It'll kind of run through that animation, giving us the most recent p-hat from the last sample. The 10th one there was 32%. But you can see all those dots there at the bottom represent each of the individual p-hats for the 10 samples we drew out of this candy machine. So they're asking us on this blank here to record what the average of those 10 sample proportions would be. Okay, now I had clicked the summary statistics box that you can see right here. And so they're telling us the average of these 10 p-hats is roughly 0.392. So that's what I'm going to put on the blank right here. It's then asking for what is the spread, the standard deviation of those 10 sample proportions. You can see they gave that to us right here. This SD is what the spread is. Okay, so we're looking roughly here about 10.3% is what the spread is. Okay. Now, we'd like to take more than just 10 samples here. So it says, let's not clear out those previous 10. We're going to keep those. We'd really like a total, though, of 400 samples. And so we need to take 390 more. If you're following along actually doing this on the web page, you could unclick the animate button, change the number of samples to 390, and when we click draw samples, it'll do that extremely quickly. It'll add all the dots on the dot plot, and you can see now that brings the total number of samples that have been taken up to 400. Okay. So this is quite a few samples. It tells us a lot as we start to look at now what's the shape of the dot plot, where does it look like the center is, we can look at the mean, and we can look at the spread, the standard deviation here. Now I kind of have this filled in for us, but you can notice that the shape of this certainly looks like it's roughly symmetrical and somewhat bell-shaped, okay, in nature. So it kind of looks like a normal curve would approximate this distribution. Okay, when it comes to the mean, that's the average of all 400 of these sample proportion of orange candies, there is a symbol that we use for the mean of all the p-hats in a sampling distribution, and it's the mu symbol with a little sub p-hat there. That means the average, not of the population, but the average of the sampling distribution. Okay, and so I'm going to fill that in. It looks like, wow, look how much closer this is to what the true population proportion is. Remember, they told us up here on the applet, we filled in the true proportion of orange candies was 45%. And when we took 400 samples, look how close the average of all those p-hats were. It was 45.2%. Okay, really, really close to 45. Okay, the spread, we're going to grab this from over here, 0.097, and we're going to fill that into the blank here, 0.097. Okay. There is also a special symbol that means the standard deviation of your sampling distribution for p-hats, and that's the sigma symbol, but with a little sub p-hat there. Okay. Now we're going to be learning today how you actually calculate the mean and what the formula is for how to calculate the standard deviation of a sampling distribution for sample proportions. We're going to do one last thing here with this applet before we take a look at those formulas. It asks you down here in step 5, how would the sampling distribution for the sample proportion of p hats change if we made the sample size 50 candies instead of the 25 that we just did? Okay, so we're going to go ahead, I'm going to reset this. I'm going to hit the reset button on the applet. That's going to clear everything out. I'm going to change the sample size to 50, so I'm doubling the size of my sample, and I'm going to go ahead and take 400 samples just right out the get-go here, and you can see that what we have is this still feels like the shape should be approximately normal, okay? Now, approximately normal is contingent on meeting that large counts condition. And that large counts condition says that you have to take your sample size times your population proportion. That's calculating the number of expected successes. That has to be greater than or equal to 10. And then this is representing the number of expected failures. That as well has to be greater than or equal to 10. Okay, so the shape should be approximately normal if that large counts condition is met. The center of your sampling distribution for p-hat should be really, really close to what the true population proportion is. Okay? So here is our formula for how to find the mean of a sampling distribution for p-hat, and it's just merely that should land right on line with what the population proportion is. Okay, something that I'll just remark here about the spread, and then we will take a look here at these formulas, is that the standard deviation of p-hat, you should notice that the spread, it should get smaller as your sample size gets larger. And that's going to cause the spread to shrink. And you'll notice that the spread on this was definitely much larger, or much smaller. You can see when the sample size was 25, our spread was 0.097. And now, looking at the applet, it's 0.07. Okay. You're going to be asked a question on your homework that's going to have you flip a few pages back in the book, and you're going to be examining, a dot plot similar to what we just constructed there in the applet. I'm going to try to give you an example similar to what you'll see in the homework here. But if you can flip your page or your notes over to the next page, we're going to take a look at how we're calculating the p-hat, which this should be relatively simple. The p-hat is obviously just the number of successes in your sample, which for the example we just did, it would be the number of orange candies in that one sample divided by the sample size, whether it's 25 or 50, and that would give you the one p-hat for the one sample that you did. Okay? Now, the formula for how to find the mean and for how to find the standard deviation of a sampling distribution, these two formulas are actually on your formula sheet. Okay? I'm going to show you where these are at on the formula sheet here in just a moment, so that we're kind of getting comfortable with where to locate them. But one thing that you want to keep in mind before we flip to the formula sheet is anytime we're talking about finding the spread, standard deviation is a measure of spread, you have to make sure that that 10% condition has been met. Okay? Otherwise, we're violating that independence. Because most of the time when we're talking about drawing these samples out, we are not replacing each selection in between drawing out the next one. Okay? And it's only safe to be selecting individual pieces from a population without replacement if you make sure that your sample size times 10 is less than or equal to the population size. It's got to be small enough that you're not making too much of a dent into your overall population, but that non-replacement isn't going to affect the independence for this. Okay, so I'm just going to flip real quickly to the formula sheet so that you can see where these two formulas are at, and then we're going to put these formulas into action here with some examples. Okay, so here's the formula sheet. It's labeled Roman numeral 3, sampling distributions and inferential statistics. This chapter, chapter 7, we are specifically studying sampling distributions for proportions, okay, here. And I'm really drawing your attention to this first row here in the formula sheet. We're just talking about drawing out samples from one proportion, not two. Okay. This was the formula for how to find the center of your sampling distribution for p hats, and it should be exactly where your population proportion is. And then how to get the spread, the standard deviation of your sampling distribution of p hats is this formula here. We will talk about the third formula in this row as it comes up, but those are the two that we just want to kind of focus on here right now. Okay, so I'm going to go back to the notes page. Actually have you just flip to the next page if you would here, and you can see summarized at the top. We have kind of the process of what it's going to take to kind of work through these problems. You're going to notice when we started in chapter 1, we were talking about describing distributions by their center, by their spread, and by their shape. Okay? And those are the three things that we need to do first with these sampling distributions. Okay? So our step 1, we want to make sure that we are identifying what is the mean of the sampling distribution, and that should be whatever your population proportion is. Okay, so let's see if we can do that. Let's walk through this with maybe these examples here, okay? The second step is finding the spread, the standard deviation of your sampling distribution. Okay? Now that is using this formula right here. And I'm just going to underline here, you have to confirm that your 10% condition is met before you begin calculating the standard deviation for your sampling distribution. Now remember, the 10% condition looks like this. We're saying if we take 10 times the sample size, that should be less than or equal to the population size. If it's not, then we cannot move forward and calculate the standard deviation because our sample size is too large to be pulling out and not replacing. And generally, we are sampling without replacement when we're doing this. Okay? The third step then is the shape piece. Okay? We can say that the shape is approximately normal if we have shown that the large counts condition is satisfied. Okay, and that would be, you have to show both of these, not just one. You have to show that the number of expected successes is greater than or equal to 10, as well as the number of expected failures. Okay, that has to be, you have to check that condition before you would use any normal CDF feature at all on your calculator. And once you have found the center and the spread and the shape from those first 3 steps, you then could move to step 4, which is where you would use normal CDF to calculate whatever the desired probability is for that particular problem. Okay, so we're going to try to work through actually just 2 problems here that'll bring this video to a close here. This is in a game of Scrabble. Each player starts by drawing 7 tiles from a bag of 100 tiles. As I'm reading through these problems, there's generally a lot of numbers they throw at you, so I like to label the information they give you sort of off to the side here. So they're telling us there are 100 tiles in the bag total. I'm going to use a capital N to describe that. Capital N is the variable we use to describe the number in the population. It says they're going to be drawing out 7 tiles from that bag, so we use a lowercase n to represent our sample size. It mentions that there are 42 vowels and 56 consonants, and then 2 blank tiles. Kate chooses an SRS, a simple random sample of 7 tiles. We're going to let P hat be the proportion of vowels that are in her sample. Okay? So our variable of interest here are the vowels. That's what we're focusing on here. So it mentions that there were 42 vowels in the bag total, So technically, I know what the true actual sample proportion is. That's 42 vowels out of the 100 total tiles. P, not P hat, is 42% or 0.42. Okay, so let's practice and see if we can check the 10% condition here and justify our answer. Remember, the 10% condition is linked to finding the standard deviation. Okay? So here's our 10% condition. I'm just going to write it generically first. On the AP test, you would not be expected to have to write that generic formula out. Okay? Our sample size we said was 7. So I'm going to fill that in there. And we said our population size is 100, so I'm filling that there. All right. So when we plug these in, we want to make sure that we're left with a true inequality statement, and certainly 70 is less than or equal to 10. So I can say yes, that it's met, and my justification is my work there showing the values I plugged into the 10% condition. Okay, so that means on this particular problem, I would be able to move forward and go ahead and calculate the standard deviation if I needed to do that. In part B, it's asking, is the normal condition met? Okay. Now, the normal condition is referring to what we call the large counts condition. The large counts condition. Okay, and that large counts condition, again, I'm going to kind of write this out generically, really just for your notes so that you have the formula there, but you would not be expected to write this out generically on the AP test. All right, so here's what I need to show in order to be able to move forward with concluding that the sampling distribution for this particular scenario would in fact be normal. Okay? And again, you have to show both of these. So our sample size we said was 7. We said the P was 42%, and I need to make sure that when I multiply 7 by 0.42, that number would definitely be greater than or equal to 10. And you'll notice that the number that we're getting is 2.94. That is not greater than or equal to 10. That's enough to say that this fails. I'm just going to go ahead and show the other side of this here. Essentially, we would be multiplying 7 by 0.58, which again, even on this side here, it's also not met. But it really wouldn't have mattered because both of these have to be met in order for us to move forward with concluding that the shape of the distribution would be normal. So I would respond to this, no, the normal condition is not met, and my justification again is really just the work that I'm showing it. Okay. So let's see if we can walk through a problem that's actually asking us to calculate a probability, and in order to be able to do that, we need to find the mean, standard deviation, and the shape. Hopefully that'll be normal. So I recopied that same information that we had on the previous slide, these 4 steps here. Okay. 1, 2, 3, and then 4. And we'll see if we can apply this to this last example here. So the polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. So I'm going to write down some of the information that they're giving us here. It sounds like their sample size, the lowercase n, is 1,500. They were sampling 1,500 first-year college students. They don't tell us what the size or the amount of all first-year college students are. So I'm just going to define the population, capital N, as all first-year college students. They don't have that value, but that is what the population does represent. They're also telling us that we're going to suppose that actually 35% of all first-year students attend college within 50 miles of home. So that's what they want us to use as our population proportion. So those are kind of the 3 givens there. Okay, so it's asking us, what's the probability that the random sample of 1,500 students is going to give a result within 2 percentage points of the true value? Remember, the true value is 35% of all first-year students actually attend college within 50 miles of home. So the question that's being asked here is we want to find, well, what would be the probability? It says within 2% here. So we want to know what's the probability that we would get a sample proportion that would be somewhere between 0.37 and 0.33, like adding 2% and subtracting 2% from the 35%. That's what the question that we're trying to answer. And before we can answer that, I'm just going to scroll back up to the top here. We need to establish what the mean, standard deviation, and the shape of this sampling distribution is, so that we can hopefully use maybe a normal CDF calculation to calculate that probability. Okay, so we're just going to kind of move through. I'm going to go ahead and label these parts here. Number one, for the mean. Okay, and now you have to be careful when you're doing this. The correct variable to use would be mu sub p hat, and that should be exactly whatever they told us the population proportion is. Okay, recall, this is a formula. It's about as simple as a formula could on the formula sheet, and it just should be the exact value of whatever the population proportion is. So I'm going to fill in 0.35. Okay. The second step is when we do the standard deviation. Now remember, before we do the standard deviation, we must show that the 10% condition has been met. So I'm going to start with the 10% condition and show that if I multiply the sample size by 10, that's going to still be less than or equal to my population size. Now we don't know what the number of all first-year college students is, so I'm just going to kind of label where my population would go, all first-year college students. And you want to look at this and really just say, does this seem reasonable? So if I were to multiply 1,500 by 10, it certainly feels reasonable that 15,000 is less than all first-year college students. Okay, so that feels like a realistic statement. So I'm going to check off that we've met the 10% condition, which means I can move forward with calculating my standard deviation for the sampling proportion. Now I'm going to use that formula that I just circled in green there. This formula is on your formula sheet. So it's not something that you will need to memorize. I'm going to go ahead and write out the formula first. Again, something that isn't necessary for you to do on the test. Okay, and then I'm going to go ahead and show, you do have to show it with the substitution. So, okay, and our sample size was 1,500. So if we were to punch that in, we would get this spread here to be roughly 0.0123. Go ahead and label over here so that I can circle that because I'll need that here later. Okay, our third step is for the shape. We look back up here. Remember, before we can make the statement that this is approximately normal, we have to have checked the large counts condition. Okay, so for my third step here, I'm going to start, I'm just going to abbreviate LCC for large counts condition, and I'm going to be showing these two things here. Okay, so with my substitutions, I need to show that that's true. And then I'm just going to fill in 1 minus p would be the 65%. And so 1,500 times 0.35 is 525, well over 10. And 1,500 times 0.65 is 975, and well over 10. So I can check off the large counts condition is met, which means my conclusion in terms of shape, I can call this approximately normal. Okay, approximately normal. So now I'm ready to actually answer the question that they were asking, which is what would be the probability that you would get a sample proportion that would be within 2 percentage points of the true population proportion. Okay? So for me to be able to answer this, I would use my calculator. Remember, it's crucial that we are always writing down what our calculator inputs are. The lower, upper, mean, and standard deviation. So our lower is our 0.33 and our upper is our 0.37. We have our mean from step 1. We have our standard deviation from step 2. We punch those into the calculator, and we end up getting roughly, there's an 89.61% chance, okay, that the sample proportion that is drawn out would be somewhere between 33% and 37% there. Two quick things I'm going to mention before we wrap this video up. There is a question on the homework that's going to ask you, what should you do to your sample size if you want your standard deviation to be cut in half? Okay? So let's just think about this algebraically here for a minute. Look at where that variable n is located. It is in the denominator and it is underneath a square root. So if I am wanting a 1/2 to appear in front here, to be cutting that in half, you have to ask yourself, what do I need that denominator underneath the square root to be? What number should that be that would produce a 2 out in front? Okay, so in other words, the square root of what number would give me a 2? Well, you would need to actually quadruple your sample size. That would need to be 4 times whatever your sample size is. That would put a 4 underneath. Keep in mind that's underneath a square root symbol, and so then that creates a 2 in the denominator, essentially a 1/2, cutting your spread in half. And we know that happens. As we increase our sample size, it does cause the spread to shrink in around what that true population parameter is. So we would always want to quadruple our sample size if we're wanting to cut the spread, the standard deviation, in half. Okay, the last thing, and this is also a homework question, you are going to be asked, if I can find where this is at here. Here we go. You're going to be asked, there we go, on the homework to look back, and I just copied an example here from when we did that Ask Reese Pieces applet here. You're going to be asked how unusual or should you be surprised if a sample proportion, I'm just going to use this one as an example, but they're going to give you a picture of this in the book. Should you be surprised if you get a sample size of, or a sample proportion to be, say, 32%? Is that very alarming? So you're going to look at this dot plot. These dots are really, really small. Okay? I think it's a little easier to tell in the book. You would need to total up all the dots above the 0.32, and then everything also that's less than that. Keep in mind, this was 400 samples here. I'm going to add these up quickly. I think that the number of dots there is around 16 dots. Okay? So that means 16 out of 400 is the likelihood that we would get a sample proportion of 32% or something even smaller than that. Okay? That comes out to 0.04. Okay? Remember, 5% is our benchmark. So anytime we're looking at something like this and we notice that that particular situation is only occurring 5% or less, then we should say we would be pretty surprised that that should happen. So in this particular picture, it would be surprising that we would get a sample where the sample proportion of orange candies would be 32% or something smaller than that. Because out of the 400 times we ran this simulation, it only happened 16 times that we got a sample proportion of 32% or less. So we would be very surprised if that happened because that's falling underneath our 5% benchmark. Now, if I asked you, should we be surprised if the sample proportion is 40%? Now we're talking about all of these dots. And I didn't go through and add those up, But, if we were to do that and figure out what that percent is, that is probably greater than 5%. That's not that surprising then. It's not that surprising. And so that's what they're wanting you to do, is take a look at all the dots from there to the left and figure out what the percent is out of the total 400. If it's smaller than 5%, it is alarming that that would happen. If it's larger than 5%, it's not that alarming. Okay, I think that brings this video to a close. You can see the few problems there that you can try for homework.